All right. Third time's a charm, as they say. This lab is osmosis and dialysis. And before we dig into the theory, we need to get a couple of things started, because it takes a few minutes for them to process. One is we need these little hot water, and this is a stirring hot plate. So we're not going to use the stir, we just use the heat, and we'll crank it up to about in that neighborhood. Should get warm pretty quick. And we also want to start soaking our dialysis tubing. It's not going to make any sense right now, but it will. But this tubing has to be soaked in order to be activated. In other words, if we try to use it dry, the experiment will fail. So we're going to glove up, not just to protect ourselves from things like the iodine solution or the hot plate, some layer of protection, but we don't want any fingerprints on this tubing. Okay, so the method calls for a 200 millimeter, I believe, yes, 200 millimeter piece of dialysis tubing. Let's get it out of here. All right, and it comes in a flat roll. Now this is supposed to be tucked on the inside. I want to use, let's see, now we can estimate. It doesn't have to be exact. That's 150 millimeters. So we need another 5 out to about right here. All right. Okay. So we'll take the tube, we'll stretch it out till it's long enough, and we're going to cut it right here. Now I keep calling this a tube, and believe me, it is, but it's flat right now. And once it's soaked and we open it up, there's space in the middle of it. So we can put this dialysis tubing away. And you just store it in a cool, dry place in its original bag and in another bag for protection. Okay. Now we just need some distilled water. So we're going to put the tube in this beaker, 250 milliliter beaker. There. It'll lay down as soon as we add water to it. And then we're just going to put distilled water in there with it. There we go. And let it soak. So while that's doing that, we've got our hot water going. Now we can talk about theory. Osmosis and dialysis. Okay, so this is what the method looks like. And it's in Blackboard, of course. So let's walk over here so I can talk with my hands and my chalk. I might need not need an eraser. Okay. So first thing, and this should be a reminder, is, let's see, won't need that yet. What is a solution? All right, I'm going to try to write down low enough so you can see. So I'm going to write down here and tilt my head a little bit. All right. So from the beginning of the semester, you remember a solution is a homogeneous mixture. So in order to have a mixture, you have to have at least 2 components. You have one, which is the major component, which is the solvent. All right, that's the major component. And then you have at least one solute. Now you can only have one solvent for a solution, but you can have lots of solutes. Okay, so now we've established that, homogeneous of course, the solution has the exact same composition everywhere in this solution. You can sample it any place in the solution, you get the same ratio of solvent to solute. Okay? And we're concerned here, osmosis and dialysis, we're concerned with aqueous solutions. So the solvent is going to be water. And we designate that with an AQ, of course, if we're putting it into a chemical reaction, a equation. Okay, so let's talk about this. Lab is concerning osmosis and dialysis. And the temptation might be to equate the two, but there are significant differences between the two. We're going to start with osmosis first. Osmosis has to do with a semi-permeable membrane. So osmosis requires a semi-permeable membrane. I don't like that chalk. So what does semi-permeable mean? Semi-permeable is the word that we use to describe a membrane that will only pass water and nothing else. So we say we have a membrane here. There's our membrane. And we have on one side of the membrane, well, let's start off with water on both sides. All right? So we know that the membrane will pass water, so what's happening now? Well, water from here is going that direction, and water from here is going that direction, right? But they're happening at the same rates because there's only water here and there's only water there, right? So there's really no evidence of change, but that is what's happening. Water is passing through the membrane, both directions, at the same rates. Okay? So what would happen if we added a solute on one side? Right? Just put something over here, like, I don't know, starch. Make a starch solution. No, let's not use starch. Because in our experiment, we're going to use table salt. So let's use salt. There you go. So now we have a solution of sodium chloride on this side and water on that side. So now what's going to happen? Well, the ability or the tendency of water to pass through the membrane from this direction is decreased for a number of reasons, one of which is that the passage of water is dependent on the number of impacts per second, say, of water molecules against that membrane. And if you have sodium chloride in there taking up space, you have fewer impacts of the water molecules on the membrane. So the velocity here going this direction stays the same as it was, but the velocity here decreases. So now the velocity of V1, the rate at which water passes the membrane, is less than V2. So now what's going to happen? Well, because this is at the original rate and this is slowed down, this is going to tend to accumulate on that side. Right? You're going to have more water headed this direction. So what happens? You build up pressure. If this is a vessel that is enclosed, and it could be semi-flexible, but it's going to build up pressure because of the added amount of water on this side. All right, so, and also down here, this is build-up pressure, and the pressure on this side is going to decrease. Okay? So, the difference between those two is what we call osmotic pressure. Okay? And that osmotic pressure is measurable. You can measure it if you have a, let's say, a tube like this. Let's see. Yeah, let's use a U-tube like this. Okay? And now we're going to put our membrane right here. There we go. So let's be relative to this diagram over here. We're going to say this side has the sodium chloride solution, aqueous. Okay? And this side has water. And we start off at the same level to begin with. Right? So now, what are you going to see? You're going to see this level drop, like that, and this level increase, like that. Okay? And the difference between those two heights is a measure of the osmotic pressure. Now, does it go on forever? Well, no, actually it doesn't. In this case, it proceeds until the pressure on this side, which also contributes to the impacts of water. If you have higher pressure on this side, then more water is going to be impacting this per second than it is on that side, simply because there's more force behind it. So it'll go to a certain height, and then the rates will stabilize. And at that point, at that equilibrium point, that's your osmotic pressure. Now, there are a number of ways to measure this, but that's one way. Okay, so now we need a discussion of tonicity. Tonicity is a word that's used to describe the relative concentration of one side against the other. So before, we had water and water only. Or if we had the same concentration of sodium chloride on both sides, we would also say that those two solutions were isotonic. Iso is a Greek prefix that means same as. You know those little bugs, those little roly-polies? You play with them and they roll up in a ball like that. Those are called isopods. Pod means foot, iso same. It's got a bunch of feet on them and they all look the same. That's why they call it an isopod. So, but in this scenario, when you have water on that side and sodium chloride on this side in solution, that situation says this solution relative to that one is hypertonic. Okay? Hyper means more than, greater than. Right? Okay. So if this one is hypertonic to that one, then this one is hypotonic to that one. This one is less than that one in terms of the solute concentration. All right? Now you can say that these terms are valid also if you have sodium chloride in both sides. But if this side is higher sodium chloride solution than that one, then this one would be hypertonic to this one, and this one would be hypotonic to that one. And that's what we have with cells, because a cell is basically a bag. One way, in fact, in the 16th century and beyond, for quite a while, cells were just used as viewed as jelly-filled sacks. But it has a membrane around it, and this membrane is, among other things, a semi-permeable membrane. Now, that's not a complete representation of the membrane of a living cell, because a living cell has both passive and active transport mechanisms. We're concerned here with the passive transport mechanism, which is the semi-permeable membrane. And to simulate that membrane, we're going to use a potato, the insides of a potato, or the potato core. We have our tables over here set up for receiving the data, and osmosis of living cells, this is where we have our potato cores. We're going to have 3, or potato cylinders, we call them in this case. All right. So, what about this cell? Well, if the solution outside the cell, we put the potato into a solution that is pure water, then the cell should be hypertonic to the external solution, and the external solution then would be hypotonic. And we usually, when we describe hypotonic, hypertonic, we're talking about the solution that surrounds the cell. Just a word of caution. While it's valid to say this one relative to that one, when the terms are used, they're usually used in terms of what's the surrounding environment. And in this case, if it were pure water, it would be hypotonic. Now, if it were a solution of salt that was roughly equivalent to the solute concentration inside the cell, it would be isotonic. And what would happen? Well, we would expect nothing to happen in terms of movement of water, because if the concentration is the same inside and out, the velocity of water travel is the same inside, going in and going out. If we had a solution out here that was much, much higher concentration of salt than inside the cell, which way would the water move? Well, the velocity in would be slowed down. So the velocity out of water would be increased, and the cell would shrivel as it loses water. If this were hypotonic, like pure water, then the water would move in, and if the cell couldn't stand the pressure that's building up inside, it would burst. That's why when a patient is given an intravenous injection, a solution, the solution is isotonic to the patient's blood and tissues. Otherwise, you will damage them, and in the extreme conditions, you could kill your patient. Okay, so that's semi-permeable membrane. Now let's talk about dialysis. Find my eraser. Dialysis also involves a membrane. And our dialysis tubing is what we're going to use to experiment with this concept. Dialysis. Okay? For dialysis, the membrane is not semi-permeable. The membrane is differentially permeable, I think is the word that the authors use. Let me see. Here it is. Differentially permeable. Differentially permeable. Sometimes you'll see this selectively permeable. They're synonymous. What does that mean? Well, the membrane under investigation allows the passage of molecules based on size. Molecules pass based on size. Okay? So there are different grades of dialysis tubing that can be used, and the size of the pores in the tubing are controllable by the process of preparing the tubing itself. And it can be rated to pass only very small molecules, or it can pass small and medium size, or small, medium, and slightly large. I mean, if it could pass everything, the tubing would be worthless anyway. So you have to be selective or differentially permeable based on size. So that's what we're going to use the dialysis tubing for. We're going to investigate the passage of two different size molecules. Glucose is one. Actually, we're using a solution of dextrose, but dextrose is a 6-carbon mixture of sugars, and glucose is a pure hexose, we call them hexose sugar. And then starch. Now, of course, glucose is a very small molecule, and starch is a polymer that's made by plants. Well, this starch is made by plants. And it is a polymer based of subunits of glucose. So this is the very small molecule, this is the very large molecule. So what should you expect? Well, if we have a membrane here, and we have two solutions, and we have glucose in solution here, and starch in solution here, right? And we just have water over here, and of course water over here. Now, water can move both directions, right? That's not a problem. But now this membrane allows other molecules to pass based on size. So which one would pass through the membrane, do you think? I would expect the small one to go through, and the large one to not pass. That's what that would be my logic for the behavior of this membrane. Okay, what are the practical applications of this process called dialysis? Well, one is called hemodialysis. Hemodialysis. Right? Hemo means blood. So, if we're going to couple hemo with dialysis, we're going to do something with blood based on the process of dialysis. Now, why would you want to do that? Well, primarily, hemodialysis is used for people who are experiencing kidney failure. Their own kidneys are not doing the job, and kidneys are just packed with differentially permeable membrane. So if the kidneys are failing and the patient is on a waiting list for a kidney transplant, then in the meantime, in the intervening time to keep the patient alive, we use hemodialysis to wash the blood, in quotes, wash the blood of poisons that the body would normally eliminate in the urine, right? One of them, of course, is urea, right, in rather large amounts. Urea is a breakdown product of proteins and nucleic acids, right? So our body has to get rid of them when it's through using the protein, digesting the protein and using it, and repairing tissues and getting rid of bad stuff, a whole host of processes. Urea. We also want to get rid of excess electrolytes in the blood, like sodium, potassium, right? There are a number of others. So we use hemodialysis. So how does it work? Well, we have a solution in a tank, and we have our patient over here. Right? There's his arm. Looks more like a cat. And blood is removed in tube and sent through coils of dialysis tubing in this solution. And then it goes back in. Let's see, if we take it out of, we probably want to go in below. Right, take it out here and send it back in. And this solution in here is specially designed so that not only will it pass small molecules like these, but it will pass only a certain amount of them. So how do we control that? Controlling the amount of poisons that are removed depends on the dialysate. This is the dialysate tank. Dialysate. It's outside the tubing. The dialysate is adjusted to be a certain concentration of the poisons that you want to remove. So what happens? Well, they can move freely back across, across the membrane, right? So as your blood moves through this dialysate, when it reaches an equilibrium place, or if you want to completely remove urea, you just have buffered water over here. And it'll take out all the urea. But if you only want to remove a certain amount of sodium here, you have a concentration of sodium here that might be a certain level, and then you have a concentration out here of a certain level, and once they reach equilibrium, then there's no more movement. And that way you can establish a correct level of the electrolyte in the blood as it washes through the dialysate. Okay. In all other respects, besides these poisons and other things that we want to adjust, the concentration of components in the dialysate is equal with the concentration of components in the blood. Now, they may not be the exact kind, but they're adjusted in such a way that this solution is isotonic to your blood in all other respects. Right? It's definitely a science and an art to helping the patients survive kidney failure. Okay, so that's our pre-lab discussion. Now let's look at the pre-lab questions, because we need to do a calculation before we can prepare our hypertonic and hypotonic solutions, isotonic solutions as well. Okay, so let's turn the pages back to pre-lab. Here we go. So pre-lab question 1 asks, let's see, let me write it down low and this camera doesn't pick up everything. Okay, so for number 1, calculate the amount of sodium chloride needed to prepare 50 milliliters of these two solutions, either 0.9% sodium chloride or 20% sodium chloride. Okay? Now, you're going to have to, when you answer this question for real and turn this report in, you got to show me this work, so pay close attention. To prepare 50 milliliters, we have to understand, what does percent mean? Right? Percent is a dimensionless number. It just means parts per 100. So what are parts and what are the hundreds? Well, the parts, the numerator is probably grams or mass. And the numerator, 100 something or other, is probably milliliters, which is roughly equivalent to grams because the specific gravity of water is 1. That is 1 gram per milliliter. So 100 milliliters of solution, and particularly if it's 0.9%, the density of the solution is not going to be changed much. It will be changed a little bit here, but we're only looking at difference between these two. So if it's grams per 100 milliliters, and you've got 0.9 grams per 100 milliliters, then how many grams does it take for 50 milliliters? It's a ratio. Just takes half. Right? Isn't that the same expression as this? Exactly, it is. How about this one? Well, using the same logic, 20 grams per 100 milliliters equals 10 grams per 50 milliliters. Okay? Now I'm going to go one step further because in the experiment we're going to prepare 25 milliliters of these two solutions. So if this is 50 milliliters, then 25 is either a quarter of that one or a half of this one, same ratio, right? So this is 2.5 per 25 milliliters. And this one will be half again as much as that one. So that's 5 grams per 25 milliliters. Now, the way we're going to prepare these solutions when we actually get over there and start doing it is we're going to add this mass of salt to that many milliliters of water. And for this preparation, it won't make a bit of difference in the concentration. But for something this concentrated, doing it that way does introduce a significant error. If we were trying to be exact with this, we would take 5 grams and add it to water in a 25 milliliter flask. Marked off there. And be sure that we had 25 milliliters of solution. Then that would be accurate. But we're only interested in the difference between this one and this one. This one is our hypertonic solution. This is our isotonic solution. And pure water is our hypotonic solution. So we only need the differences are important. So even this one's not exactly 20% sodium chloride. It's less than. But it's still hypertonic. All right? Okay, so that's pre-lab 1. Second question is define isotonic, hypotonic, hypertonic. We've already done that. You can fill those in. Let's see. 3, describe the function of the dialysis tubing. I just did that. Well, in this experiment, what are we trying to do with the dialysis tubing? We're trying to simulate for instance, what would the dialysis tubing be used for? Right? And this is one major uses. I can see this very faint here, hemodialysis. That's one possible. What's the purpose of the Benedict's test? Okay, now we're talking about, and this is number 4. What's the purpose of the Benedict's test? Benedict. I'm sure it's named after someone. Benedict solution. The Benedict solution detects, in our case, it detects glucose. But the chemistry is actually, it detects reducing sugars. And in order to be a reducing sugar, you need a carbonyl group, which in chemistry is anything bound to carbon, and then it has like that, and usually like this. So that's a carbonyl group, and it's a reducing group. So that's what this detects. But you don't need to know that for this lab or for the future. That's just if you're curious, you can look it up and read some more on it. And number 5, what's the purpose of the iodine test? Right, so we'll use iodine, right, elemental iodine in potassium iodide solution, right? Those two together. What does it detect? It detects starch. Now, I forget the man's name who discovered it, but it was back in the middle 19th century. Discovered that starch could be detected by this mixture, and it was immediate at room temperature. Now, the theory is that the starch molecules, they form a helix at room temperature in solution. And if you have this ion, a triiodate ion, it will fit neatly in there. And when it does that, the conformation changes, the light absorption properties change, and you get, in some cases, a deep dark blue purple. It's a little bit different for our experiment, but it's immediate and noticeable and identifiable. It has to be this. This one won't work. This one won't work. That's why they're in that solution together, because together they form enough of this. They combine, it's a reaction, to give you the triiodate ion, and then you get your reaction. Now, the exact chemistry behind it is still a mystery, but it's used to detect starch. And if you take some of that solution and drop it on a piece of bread, you'll instantly get a blue-black color. All right, so now we need to get on with the experiment. And I need to take a moment and check my battery because this thing is going to poop out on me. I just know it. So pardon me while I look. Okay, we're still recording, so that means, and I've got about half a battery life, so I need to be careful. I shouldn't go more than 10 minutes before I change the battery in this little camera. Okay, so now we have everything we need right here. Our water is just beginning to start to boil, so it'll be ready. We got a soaking dialysis tube. We have our potato. We have our glucose solution. We have our starch solution. We have our iodine. We have our Benedict solution. You may wonder what's in there. What gives it that blue color? Copper. Copper makes it blue. We have other utensils. And I'll point things out, the slight differences in the method that occur as we proceed. We have our analytical balance, we have our table salt, and this is salt from great value. What's that? Walmart. But it has no iodine in it. You can use the salt that you get in the store is very pure, except if it has iodine in it. And for general purposes in the lab, you want salt that has no iodine in it. If you want iodine in your reaction, you add it separately, where you can control. Okay, so next thing, we want to prepare 25 milliliters each of two solutions. We're going to take 3 100 milliliter beakers and label them. The first one is for a cylinder. Potato cylinder 1 is 20% sodium chloride. So we'll just mark that on here. 20%. And this one we'll mark as 0.9%. And this one is pure water. Okay. So we need to do these two by measuring out the salt. Now, we already did our calculations, right? So to make 25 milliliters of 20%, how many grams do we need? 5 grams in 25 milliliters. So let's measure out 5 grams. We could do it straight into the beaker, but I'm going to do it this way just because I feel like it. So put that on there, and then we hit this tare button, which means it subtracts the weight of the container and re-zeros. So now anything we put in that container is registered here as the actual weight of the contents of the container. All right. So we need 5 grams. And since our concentration is not exact, it's not really accurate, we just need to get close. In fact, if we go over a little bit, it'll be closer to 20%. Okay, so there's, and the nice thing about these boats is you can make them into sort of a funnel. So we just squeeze the edges, notice, there we go. We're going to knock off as much as we can. All right. So that's the salt for the 20%. Now we need the 0.9%, which was 0.225. Right? 0.225. I think it's going to be more efficient to put a little bit in here, like that, and then use a smaller spatula. And the reason I want to use a plastic weigh boat is because these balances, right now they're registering 3 decimal places of grams. But if you put a heavy mass in there and try to tare it, it'll automatically chop off the last decimal. So if we use the lighter container, we're more likely to get that 3rd digit that we need, 0.225. Okay, let's zero it. Now, let's get this one as close as we can. Oops, I went over. All right, so hold on a second. It's not going to let me get it. Let's use this one. See if it'll do it. There's a lot of static electricity in this plastic. All right, here's what I'm going to have to do. I'm going to have to dump a little bit of it out. There we go. Well, that wasn't even enough. Okay, now we're back down below. I can be a little more careful this time with just a few grains at a time. Very delicate. Close the lid. Right on the money. 0.225. Okay. Now this one, we need to transfer everything. It wasn't as important for the higher concentration. We need to get everything in this one. So we're going to need 25 milliliters. This is a 50 milliliter graduated cylinder, and 25 is right there where my thumbnail is. Okay? So let's get 25 in here, and we'll do the 0.9% first. And let's hold it eye level. Not eye level for you, of course. And bring it right up to 25. Now what we're going to do is we're going to add as much of this dry as possible, and then get the last of it by rinsing small amounts. It's visual inspection. Yep, I think we're good. We'll put the rest in here. That's what's known as quantitative transfer. Okay, that ought to dissolve fairly quickly. The 20%, in fact, may not dissolve completely. It could be almost saturated. Okay, there's 25. There we go. Okay, 25 milliliters. And we'll finish it off with a wash bottle. 25 is right about there. Okay. Okay. Now, I'm going to use this stir rod after I rinse it off. Can't be too careful. And just help this 20% along a little bit. Let me turn this down just a hair. Okay. Now, in the third one is just pure water, right? So, in fact, it doesn't even have to be exact. Well, let's be exact. Right. Let's check the value here. There we go. And we don't have a variable in volume size. It's all the same volume. Okay. So there are 3 solutions for the potato. All right, so we made those. That's step 1, part 1, step 1, 2, okay. And the next thing we're going to do is take our cores out of our potato. And I'm going to take a short break, pause the video, and I'll be back in just a second. Okay, I'm back. And the battery change came just in the nick of time. Now let me re-glove. And now we're ready to cut our cores. So in order to cut a core from this potato, we need a fresh surface. So I'm going to split it probably close to the top, so we'll have plenty of room, because we need 40 millimeters. Right? So that I need to cut it as close to the top as possible, and then core it this way. Okay. So I got a razor blade, but I'm going to use my trusty pocket knife. And we're going to perform some surgery on this potato. Here we go. There. Now, never put a dirty knife back in its sheath. All right. Now, we also need containers for each one of the potato cores. All right, so this one's going to be for the 20%. This one's going to be for the 0.9%. This one's going to be for the water. All right. Okay. Just thinking. I always like to stop and think so I don't make a mistake, because some mistakes you cannot recover from. All right. So let's get our cores. We're going to use a cork borer. This is just punching holes in corks. And it's 2 millimeters hole size. All right. And this, of course, is for pushing the core out once we make it. Okay. So the trick to these is coring from the same type of tissue for each one. And it looks like if we go between these radiating lines, we'll get a similar composition. So let me go down through this one right here. And we're just going to go all the way out the other end. Here we go. We're just going to get 3 cores right off the bat. And another one right here. Now let's see, are these long enough? Oh yeah, plenty of room to spare. We can trim. Okay, one more. Let's try this one from right here. Oop, I left that one in the hole. Let's do another one. Go all the way through, out the other side. There we go. Now, I hope this one's long enough. Let's check it. Oh yeah, we're good. So that's the potato, which is no longer needed. And we just do a preliminary surface drying before we weigh it. And what we want to do is trim to as close to 4 centimeters, 40 millimeters as possible. So if we set this one on 40 right here on the right hand edge, and then come down right on the 0 mark, I'm hoping that we can get exactly 40. Refine my mark. So let's remeasure it. Exactly 40. So let's use tweezers. And contamination. You know what? Let's rinse it off and then dry it off again. There we go. So what's the texture here? Well, let's see. It's firm but pliable. Yeah, so all of them should be the same, firm but pliable. And what we want now is to get the weight of this. So I'm going to tear that container. And then get a weight. Or a mass, actually. Let's see. You know what? I just remembered. First thing we're going to do is find out how much does this container weigh. We're going to get the tare weight on that. Then we can reweigh it later. We won't have to tare it at all. We can always subtract the weight of the container from whatever mass we get. Okay, so I have to re-zero it, sorry. Now, what's the weight of that container? 2.609. 2.609 is the tare on cylinder 1 container. There we go. Now, we're just going to put the cylinder in the container and get the weight of the container plus the cylinder. And then the cylinder will be the difference between the two. 2.956. This is before soaking. 2.956. And then the difference between these two is the mass of our cylinder. And we can do those calculations later. Right now we want to get this thing rolling. So let's set this one over here. All right, and let's do 0.9. All right, and while that's coming to equilibrium, we're going to take this one and cut out a 40 millimeter length. Okay, there we go. Let's see if I can perform magic again. Here we go. Now let's measure it. Right on the money. So this one is also 40 millimeters. Oh, 2.649. 2.649 is the mass of the container. 2.649. Now we need the combined mass. 2.99. Ooh, it's jumping around. I'm just going to have to pick a number. 2.995. Okay. And one more. So let's get our blade out and see if we can perform a hat trick. Okay, did we do it? Right on the money. 40 millimeters. Oops. 0. Okay. And the tare for this one is 2.664. Now, the mass of both combined, 3.01, jumping around. We're just going to have to pick an average, 3.011. Okay, the length for each one of these is 40.0. Remember that last digit is an estimate, millimeters. The texture is firm, yet pliable. And that's each one. Okay? Now we can start the soaking. All right. So let me get my stopwatch out, which is actually my phone. Here we go. And I've got an app here with a timer on it. 45 minutes, right? Let me check. Yep. After 45 minutes. Okay. So what we're going to do is, in just a second. Yeah, that's not all in solution, so that 20% sodium chloride may be saturated. All right, so the concentration won't matter really. Whatever saturation is at this temperature. Okay. So let's clean that off. Discard the scraps. Actually, we can throw a potato away too. Okay, now we're going to transfer each one of these into its container. And to protect them from contamination, we're just going to cover them like that. All right, and then we're going to set these aside for 45 minutes, starting now. There it goes. Now the only problem with this is it's kind of close to that heat source. So let's make an adjustment here. There we go. All right, so I'm going to need these two hot, and this is my backup. So I'm going to fill it up way up. It's already going to be hot if I need to reestablish. Let's turn the heat up. We need a little bit more liquid in there. This is such a small volume, it shouldn't take long to heat that up. Okay, next, while that's happening, we're going to go to part 2, dialysis. And we're going to use Benedict solution and potassium iodide and iodine to test for components. But we need to know what is the positive test going to look like and what is the negative test going to look like, because we're judging whether it's there or not. Right? So while you're thinking about that, I'm going to check my battery. And it looks like we're good. We can keep rolling on this experiment. All right. So we need to obtain Let's see. Oh, I'm ahead of myself. What we're going to do first is set up the dialysis tubing to with our starch and glucose solutions inside the tubing to see if it moves out into the dialysate surrounding the tube, surrounding the dialysis tubing. And that needs to sit for 25 minutes, I believe. So we got to set that one up first. So let's do that, and then we'll do our test solutions. Okay, so let's move this aside. Get our dialysis tubing here. All right, get the chalk dust off my fingers. In fact, there we go. Now, so how do we handle this tubing? Well, we need a test tube that's big enough to hold the tubing, and this one I believe is. Let me be sure if it's the same size as the one in the method. Yep, 20 millimeters wide at the mouth and 150 millimeters long. So it's the exact one that's called for in the method. And we're sitting in this 250 milliliter beaker just to hold it. That's just a stand. Okay, so we're going to take this tubing and tie a knot in the end. So let's pull it out. It's pre-soaked. I'll pull this out and tie a knot in one end. All right, so the best way to tie a knot is to have something round, not flat. So we're just going to flatten and flatten and fold and flatten and fold. And then we can tie a knot in the end. This is the art part. All right, there's my loop. Let's see if I can snake this through the loop. And there it is. So now we've got a knot in the end of that tubing. Okay? And we're going to open it up now. Open it up. Try it with our fingers first to see if we can get it open. Yeah, I feel it give. Now we've got access to the interior of the tube. And let's use our stirring rod to help get down inside there. There we go. All right. We're going to sort of use that stirring rod as a guide too. Now what does it want us to do? 0.25% starch solution. Fill the tube about halfway. So here's our potato starch, 0.25% potato starch. All right. And let's fill it about halfway. Let's see what's halfway. Halfway. We still need to leave a little bit at the top to tie off. So that's good. And fill it the rest of the way with our glucose solution. Within 25 millimeters of the top. What's 25 millimeters of the top? About an inch. Because 25.4 millimeters is exactly an inch. All right. So let's leave ourselves an inch at the top to tie it off. I got to get this down in there so it doesn't squirt back out. All right. There we go. Now we can pull that out. Rinse it off in a second. All right. Now there's our tube filled with the solutions. Now let's tie it off, and one of the best ways to tie it off is with a string. If we were set up for it, we would have tubing clamps, just special clamps that go, and they ratchet closed, seal it off. Slicker than snot. But this is a chemistry lab, and that usually occurs in anatomy and physiology. So we have to improvise. So let's go down here and tie it off, just like that. I don't want to set it in the tube yet, and I'll show you why in just a second. All right? Okay. And here's what I'm going to do also. I'm going to trim the excess down to about right here. And what I'm thinking of is contamination. I may have spilled some on the outside, and that would bias my results because it'll already be on the outside, and we can't claim that it came from the inside of the tube. Right? We got a little bubble in there. We call that a mixing bubble. So that mixes all the solution, and now we're going to wash it down like that. Wash anything off the outside that might have contaminated the surface. Okay. Now, of course, we don't want all this string to go along with us, so let's cut that, and I'll pick it up later. All right. So now, let's see. Okay, I missed a step. I need to add water. Half filled. We need to put water in the tube. And it says about half full. That should be enough. And now that we've rinsed off this tube, we can insert it in the dialysate. There we go. Just turn it around like this. There we go. Now we can set that aside, like here. And that's going to take 20 minutes. So my timer is, we've used 10 minutes to do that. My timer is 35, so 20 minutes would be at 15 minutes. We'll open that, run our tests, and should be finished before it's time to go back to the potato cores. All right. I've already got the hot water bath going. So let me back off the temperature a little bit so we don't boil everything away. Just needs to be hot enough to keep it boiling. How about that? 120 degrees centigrade. Okay, now we're going to do our tests for what does the solution look like when it's a positive test or when it's a negative test for both Benedict's and for the iodine. All right. So instead of the, this is step number 17, instead of the 12 by 75 millimeter tube, I have a 15 by 85 millimeter tube. 15 by 85, and it'll work perfect. I've done this before. Okay, so for the first one, testing for glucose, and I need to label one as negative control, and I'm just going to put a minus on it. Actually, I need to put a B above it for Benedict's. Benedict's minus. Negative control and Benedict's. Benedict's positive control. Okay. So, next we need to put 8 drops of distilled water in the negative and 8 drops of glucose in the positive. Okay, so we need droppers, one for each. We don't want cross-contamination. So there we go, there we go. and we need water. All right. Here we go. Let's be sure there's nothing residing in that. Eight drops. For the negative control. Here we go. There is 1, 2, 3, 4, 5, 6, 7, 8. That's water. And this one is glucose out of this bottle. So it's a wash bottle, I know, but you can't control the drops as well with a wash bottle, so I'm going to use a dropper. All right. 8 drops. 1, 2, 3, 4, 5, 6, 7, 8. All right. Here we go. Now we need Benedict's solution. 4 drops each. So for the negative control, 1, 2, 3, 4. And positive control, 1, 2, 3, 4. All right. Now what we need to observe is before we heat it, this reaction is activated with heat. All right. So we notice that the two solutions are the same color, very light blue. Right? Light blue color for both the positive and the negative control. So let's put that in our table. Negative and positive controls before we heat them. Light blue and light blue. All right. Now we already know that the negative control has no glucose. It's absent. And the positive control does have glucose. Right? So we can check those off. Now we want to observe the color after the reaction, which takes 3 minutes. If the water's boiling. Did I go too far? Let's crank it back up a little bit. Because the color goes through stages. Right? And we can get it started already. So there's the negative control. There's the positive control. And we'll just watch and see if anything happens to either one of them. I see something happening in the positive control. I hope the camera is catching it. I'll move my head around. See the change occurring at the surface, and now it's deeper in the solution, probably as the temperature rises. So it's going through a stage. First stage is orange, light orange, right? Now that's characteristic of a progression of the reaction. It's also characteristic of concentration. So if we had very light, very little glucose in that solution, this is 10%, that's a lot, even diluted. And if we had a very low concentration, like maybe 0.1%, the color may stop developing at the orange stage. Right, so that's a bit of information that I don't think they gave you in the procedure. But since this is really concentrated, we're probably going to see it progress to something different than orange. And it looks like it's continuing to progress. The water is starting to boil again, so I think it's warm enough. I didn't check my time, but I think we've probably gone through maybe a minute and a half. We'll just watch it. And let's see. While that's going, we can prepare tubes for the iodine test. So for the iodine test, we're going to do starch. All right? So we need 2 more tubes. All right, we're going to set those over here on this side. And one's going to be starch negative and starch positive. And we need the same amount as before. Distilled water. This is distilled water. Pipette. So we'll do 8 drops in the negative control for starch. 1, 2, 3, 4, 5, 6, 7, 8. And we need another pipette, a fresh one, for the actual starch solution. I see it's progressing. All right, it's past orange. All right, it's even got some precipitate in there. It's brown precipitate. Okay, 8 drops in the positive starch. 1, 2, 4, 5, 6, 7, 8. Okay. And then we need this iodine solution. It's going to take a fresh dropper. And before we do that, I'm sure it's been 3 minutes now. So let's look at our solutions. Let's turn the temperature back down so we don't boil away all our water. Just set it on 100. Okay, so the negative control is still blue, and the positive control is what? I call it brown. Let's see if my eyes have deceived me. Actually, it's not. Brown. Actually, right, olive green. Right? Brown, olive green, either one works. We'll just put both of them because I am of 2 minds. So after heating on the negative control, we're still light blue. And positive control is brown, or some way of saying, maybe considered it olive green. But remember, it went through a stage of orange, so keep that orange in mind. And let me check my battery. Okay, we're good. Still got half a battery left. Now we're going to do a positive-negative control test with iodine. So iodine test doesn't have a before and after because this reaction is instantaneous. Once you add the iodine, you will see a difference. You should see a difference. Okay, 4 in the negative, right? 1, 2, 3, 4. And in the positive, 1, 2, 3, 4. Okay. So let's keep this one next to that bottle. So what's the difference? Well, let's see. Last time I did this, I thought it was kind of an orange color, or an amber was the negative control, dark orange, and then dark brown, very dark brown for the positive. Right? Almost black. Dark brown to black. Okay? So for the starch, the negative control is orange. Dark orange, actually. And the positive control is dark brown or black. Okay? And we know this negative control has no starch in it. Positive control does have starch. Okay? Now we have our controls. We know what colors to expect. Now we can run. Well, we're not quite ready to run the experiment, but we do have our test solutions finished. All right, so now that we have that done, we have to test the dialysate, but it hadn't been in there 20 minutes yet. It needs to be down to, let's see, it was on 35 and we needed to go to 15, I believe. So 5 more minutes. Okay, so what I'm going to do is, to save the battery, I'm going to stop the video and come back in 5 minutes. All right. So now it's been 15 minutes, 20 minutes since we put the dialysis tubing with its contents to soak in the water. Okay. Just do a little bit of mixing. So, what are we supposed to do with it? Okay. It doesn't say how to open it or how to do anything with it. So, we're going to improvise. We don't want to get any of the contents of the tubing inside the dialysate. So to avoid that, let's conduct this opening outside that tubing. Okay? Because we know what's going to be inside the tubing. We don't know experimentally, we haven't proven what's in the dialysate. Okay? So to open it up, we're just going to nick it there. Notice it's bleeding on us. Okay, that's okay. As long as it occurs not in the big tube. Okay, let's stay clean here. I did forget to do this one, didn't I? So let's clean it off. There we go. All right, we don't need that in the way. Don't need that in the way. Now, so we need 2 tubes. And this is going to be, actually we need 4 tubes. Let's do 2 at a time. We're going to, this is Benedict's. All right, Benedict's. Testing for glucose, and the we're going to label this dialysate, D for dialysate, which is outside the tubing, and I for inside. All right. Okay. So let's back like that and just get these out of the way. Right, that's Benedict's. Now we also need 2 tubes for the iodine. Right. So for the iodine, actually, this is going to have an I and an I for inside. Inside iodine and dialysate iodine. Okay, so there's inside and dialysate. There's inside and dialysate. Oops, backwards. Let's be orderly. Okay, so we're going to go, I'm going to do dialysate first. It says do the other one, but I'm bucking tradition here. Okay, so dialysate goes 8 drops. 1, 2, 3, 4, 5, 6, 7, 8 for the iodine, and for the Benedict 1, 2, 3, 4, 5, 6, 7, 8. There we go. Just drop that in there. And now let's do inside the tubing. And let's just have to get it open. It's being stubborn. Let's see here. There we go. Now, 8 drops of the inside solution. 1, 2, 3, 4, 5, 6, 7, 8. And inside for iodine. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Just leave it like that. Okay, so let me get back to the method and do the analysis in the order they require. Okay, this is step number 20. Test the dialysate surrounding the dialysis tubing with potassium iodide, and that's 4 drops each for the potassium iodide. So we're going to do the potassium iodide first. Nope, excuse me. 19. No, we're going to do Benedict's first. So I need to reheat this stuff. Okay, we're going to have to do them backwards because I forgot to start the heating again. So we're going to do the iodide first. Simply because I messed up. So we need 4 drops of iodine in each of these. 1, 2, 3, 4. And 1, 2, 3, 4. There we go. We're waiting on that water to heat up. We'll do the test for starch with our iodine solution. All right. So inside is as suspected. Inside is our dark brown to black color. The dialysate is the orangish color. So no starch found its way into the dialysate surrounding the tubing. So let's make that note on our chart. Potassium iodide, testing for starch. Okay. Dialysate outside the tubing is orange. All right. And orange means negative control, absent starch. The other one is, that's almost black. I'm just going to call it black. And that means that starch is present inside the tube, which is fortunate because if it weren't in there, then we would have destroyed matter in violation of one or more laws of the universe. Okay, so now are we warm enough? Looking for evidence of boiling. Yeah, it's getting there. By the time we get the Benedict solution in here, it should be ready to heat. All right, so there are the inside and the dialysate. We'll put 4 drops of Benedict's. 1, 2, 3, 4. And 1, 2, 3, 4. And, oh, while we're waiting, we do need a before color. So before, on both the dialysate and inside the tubing, we have, let's see, background, light blue. Same for both. Okay, now we're going to heat it up and see what the Benedict's test tells us about the dialysate and the solution inside the tubing. There, we're boiling. So let's put our tubes in there and then check my watch this time for 3 minutes. Okay, what's happening? Oh, I see the one inside the tubing is already starting to change. All right. It's going through its orange stage. The one on the right is just started. So it's a little behind the one on the left, which is the inside the tubing. So the dialysate is on its way. Both of them are on their way. Actually, looks like the dialysate's moving faster. Okay. I wonder if there's... Inside the tubing also has starch. I wonder if starch partially interferes with the reaction. And the dialysate has glucose exclusively with no starch. We just tested for the starch and there's none in the dialysate. So maybe the presence of starch slows the reaction. Or it could be starch can hydrolyze at elevated temperatures, which means break apart into glucose. But I think the reaction is such that, oh, yeah, that's right. We're testing for reducing sugars or glucose. So if the heat tends to break down the starch, we would have more glucose than we would expect. But there's no starch in the dialysate outside. I mean, there's none to start with in the dialysate. So any glucose that we find in the solution outside the dialysate has to be due to migration of, one more minute, migration of glucose through the differentially permeable membrane into the dialysate. Okay, the solution from inside the tube is already now a kind of a olive green, sort of a, actually it's, yeah, it does look olive green, doesn't it? Okay. Now that's more what we would expect. Olive green. I tried to tilt my head back so you guys can see it. The one on the right, the dialysate, color changed to orange and stopped there. And it's been 3 minutes. Okay, so we can turn that off. We don't need the heat anymore. Pull these out. They're a little warm. Now let's take a look at the color. That's definitely olive green for inside the tubing, and this is orange for the dialysate. So let's put that in our chart for the Benedicts. Benedicts. The dialysate is orange, which means that there is glucose there. There's just a small amount of glucose. That's not actually. It's low amount of glucose. Inside the tube, we're olive green. That's definitely olive green. Okay, present. Okay, so we got those fixed, and it's probably getting close to time to test our potato cylinders. All right, so let's clean up some of this mess here. Just put that right in there. Slide these out of the way. And 15 seconds to go. So let me check my battery. I don't want it to run out in the middle. It's getting low, so I'm going to stop the video and change the battery, and I'll be right back. I'm back with a fresh battery, and we can proceed with the potato cylinders. All right, so now we need to go back to step number 8 in your printed method. And step number 8 is where we pick up the potato cylinders again. All right, so it's been 45 minutes. We need to bring the cylinders forward here. Let's see, let's put them in the correct order. Yes, that's water. Okay, there we go. Now, let me get another paper towel. And let's set these right here. And right here. And there we go. Okay, so for the 20%, all right, for the 20%, we want to, let's see, are they telling me exactly what to do? Blot the cylinder, yes, and reweigh it. Okay, so I need tweezers to pull it out. And let's put our, let's set this, that's on 0. So let's pull out this one. And we just want to blot the surface. Bam, that's limp. That is extremely pliable. What's the word? Very soft and limp. Okay, now we can weigh these together in the boat because we know how much the weigh boat weighs. We got that tare value earlier. So we just weigh them together. And it turns out to be 2.888. And this is cylinder 1, 2.888. 2.888. And the length, we don't know yet. The texture is soft, limp. Okay, so let's get a length on that one. how long does it happen to be? Lay it out here, try to get it straight. There we go. Now, in fact, let's push it up against. There we go. Let's see, set that on the 0 mark, and this one is 3.567. Let's see, this is in millimeters. Okay, 37.5. 37.5 millimeters. So it did shrink in length. All right, so now we get the 0.9%. We're done with this one. All right, let's put that there, out of the way. This one, when we pull this out, and it feels it's the same as before we put it in there as far as texture goes. All right, we just roll and roll. We don't want to soak water out of the center, but we do want to get the water off the outside. And we're back to 0, yes. Weigh that. And we'll also write down the texture is the same as before, firm and pliable. 2.975. 2.975. So we did get a little bit of change. So what does that mean? That means that solution was probably not isotonic. Plus, we could have made some calculation errors. Okay, and it's also firm, yet pliable. All right, we need a length. Let's get a length. All right, so let's set that right on the mark there, right there. Hold it steady while I move it up. Here we go. That's a little off the end, so let's move it back some. There we go. Yeah, it did shrink a little bit. Okay, I've got 39.0. 39.0. So it did shrink a little bit, kind of like this one, only not as much. So what that tells me is that if this is hypertonic, this is extremely hypertonic, then this is slightly hypertonic to the potato. Okay, that one's done. Now we need to do the hypotonic solution. So let's take this out, let's pull this out, and see what kind of texture. Oh man, very stiff. Solid and stiff. Let's get a length measurement while we're here. Okay. Set it right on 0 end, and the other end is 42.0. 42.0. Let that come to equilibrium. 42.0 length. All right, so 42.0 is the new length, and it is stiff. very firm. Okay, now we just need a mass value. 3.062. 3.062. 3.062. So it did gain some mass. All right, so all that's left in this chart is to actually calculate the mass of each of the cores before and after. And then there's another calculation I want to do over here called percent change. Now, I didn't say percent change of what, mass or length. So since the original length was exactly the same for each one, we could just look at the difference. Like this one got shorter, this one a little bit shorter, and this one got longer. So let's make this percent change mass. Okay, so we're going to compare the percent change for the masses as soon as that calculation is done. But we need to, actually that's it. All we have left now is post-lab questions. That is done. Done and one and done. Okay. So let's see. Post-lab question 1. The 3 solutions used in this portion of the experiment were of different tonicities, right? The sodium chloride solutions. Identify which solution was which. So you just say which one was isotonic, which one's hypotonic, which one's hypertonic. Describe the effects of each solution in the texture, masses, and length of potato cylinders. So there, you say, all right, these are the results we got for each one, and you may want to introduce the percent change of the mass as a confirmation of what you would expect from the potatoes soaking in the different solutions. Explain the effects listed in your answer number 2 in terms of the movement of solvent. So when we put a potato core in distilled water, which way is the solvent moving? And what is the solvent? Water, of course. So in distilled water, which way does the water move? Into or out of the potato? And is that supported by the evidence? Same thing for 0.9%, 20%. You may make note of the discrepancy in 0.9% because you would expect that one, if it were isotonic, that there would be no difference before and after on either length or mass. What type of solution, isotonic, hypotonic, or hypertonic, would you use for an intravenous injection of an antibiotic? And explain it, right? I told you that a little earlier, so you go back and look at the video. What conclusions can you draw from the results of the following tests you performed in Part 2? Benedict's test. What conclusions can you draw from the Benedict's test? Benedict's tested for glucose, right? So did glucose move through the differentially permeable membrane? What does that tell you about the membrane? Think about the membrane and its pore size. It's differential based on pore size. So if the glucose goes through it, then you would expect anything smaller than glucose to get through. Now, we don't know exactly where the cutoff is because glucose and starch are radically different in size. But you do know that anything less than glucose will pass through. Iodine test for starch. We found that no starch made it through the membrane. That means starch size or bigger won't get through. The limbo, the intermediate part between the two, glucose and starch, is where you're not sure where the breaking line is. All right, number 6. What size molecules diffuse through the dialysis tubing? Well, I just gave you a discussion of that one. 6 part 1, 6 part 2. What size molecules remain inside the dialysis tubing? That's more of that discussion. What type of membrane is represented by the dialysis tubing? Right? We discussed that at the very beginning. Give an example of this type of membrane that could be found in your body. Aha! The body has lots of different membranes everywhere. Right? We talked about one. Cell membranes. Right? But that's not the only one. Of course, well, there are some membranes that are not directly related to the cell wall. But where would you find these membranes? In what organs? And what tissues? You can even look that up on the internet to see if you find any information on that one. Okay, that's it. Osmosis and dialysis, done.